Welcome to our journey through artificial neural networks, pivotal in current machine learning. From their biological roots to their application in solving real-world problems, we'll delve into the inner workings of these remarkable systems. Join us as we unravel the concepts of weights, biases, and activation functions and uncover the transformative potential of deep learning. Artificial neural networks, or ANN, are powerful machine learning models that can handle various types of data, including tabular data, texts, and images. Originating from principle dating back to the 1950s, ANN experienced a significant rise in the early 2010s, leading to the immense success of today's artificial intelligence. Deep learning, often used interchangeably with ANN, refers to complex artificial neural networks with multiple layers. Before we delve deeper into ANN, let's draw inspiration from biology. Neurons, the fundamental units of a biological neural system such as the brain, communicate through electrochemical signals via synapses. Learning in the brain involves creation of new connections between neurons in our early childhood and strengthening or weakening these connections throughout our whole life. Now let's introduce the perceptron, the cornerstone of artificial neural networks. Proposed by Frank Rosenblatt already in 1957, the perceptron mimics the behavior of a biological neuron. Mathematically, it involves a weighted sum of inputs along with a bias term computed through a step function. If the weighted sum surpasses a certain threshold, typically 0, the neuron fires an output signal. Through training cycles, perceptrons adjust weights and biases and gradually improve their ability to classify data, guided by a so-called learning rate and the number of epochs. A single perceptron serves as a binary linear classifier. Activation functions determine a perceptron's output. Originally, the perceptron employed a binary step function, outputting either 0 or 1. In current artificial neural networks, various activation functions are utilized, enabling diverse perceptron outputs. The choice profoundly shapes the network's behavior. Multilayer perceptrons extend the capabilities of perceptrons by combining multiple perceptrons into one network. The input layer receives input values, while the output layer generates output values. In between is the hidden layer, where multiple perceptrons collaborate, enabling the learning of patterns. Typically, multiple hidden layers are employed. The information flow within multilayer perceptrons is direct, moving from input to output. That's why we call it a feed-forward network. Multilayer perceptrons are useful across many domains, such as image recognition, natural language processing, and predictive modeling. Deep learning takes neural networks to new heights by introducing multiple hidden layers. This makes it possible to directly process raw data, extract features, and to model intricate relationships in the data. Deep learning networks may have thousands of layers with a total of millions or even billions of trainable parameters. Due to their complexity, deep learning networks require vast amounts of data and computational power for training. It's crucial to note that not all deep learning networks are identical. In subsequent units, we will learn that there are multiple different deep learning architectures for different use cases. Today we learned that artificial neural networks inspired by the brain's workings utilize weights, biases and activation functions to process data and make predictions. From the foundational perceptron model to multi-layer perceptrons, these networks find applications in diverse fields, driving advancements in artificial intelligence.